Hi everyone. In the last lecture, we have discussed the vibration spectra for the diatomic molecule. So here in this lecture, we are going to discuss vibration rotation spectra of a diatomic molecule. This is the lecture number 10 of the investigation of the molecular structure. So here the vibration rotation spectra. So all of you know that here when we consider the diatomic molecule, generally the pure vibration spectra is not obtained in case of the diatomic molecule. Actually it is a vibration rotation spectra. So let us consider when the gas phase molecule absorb IR radiation, in addition to the vibrational energy change of the molecule, its rotational energy may also changes. So friends, here when we consider the energy of the diatomic molecules, so here all of you know that when we consider the energy, so here electronic energy level, it contains the vibrational energy levels, and vibrational energy level, it contains the rotational energy level. So here when there is a change in the vibrational energy level, at the same time there is a change in the rotational energy level in case of the diatomic molecule. So here moreover each absorption band which is due to particular vibrational energy change is found to be consist of number of relatively closed absorption line. These lines are due to the rotational energy changes occurring simultaneously along with the vibrational energy changes, and such a system it is a term as the rotating vibrator or rotating oscillator. So here when the molecule when it interact with the IR radiation, at that time there is a change in the vibrational energy as well as at the same time or simultaneously there is a change in the rotational energy. So here the pure vibration spectra is not obtained, actually it is a vibration rotation spectra. So here the micro radiations bring about the change in the rotational energy of the molecule. The IR radiation can change the vibrational energy of the molecule. The energy of the radiation is larger than the micro radiation. When IR radiations are interacting with the molecule, the always bring simultaneous change in the energy of the vibration and rotation of the molecule, thus the pure vibration spectra cannot be obtained. So here when we consider the diatomic molecule and when we consider its vibration spectra, actually it is a vibration rotation spectra. So diatomic molecule may be assumed to execute rotation and vibration independently. If there is no interaction of the vibration and rotation, the total energy of the vibrating rotator would be given by the sum of the vibrational and rotational energy. Friends, when we consider the internal energy of the diatomic molecule, so internal energy of the diatomic molecule, it is equal to the electronic energy plus vibration energy plus rotational energy. So here when we consider the vibration spectra, at that time there is a change in the vibrational energy as well as there is a change in the rotational energy. So here the total energy is equal to that is a epsilon vibration plus epsilon rotation. So here this is called as the Born-Oppenmeier approximation. So here once again in the last lecture we have discussed that is a epsilon j centimeter inverse, that is a b into j plus 1. So here the j is the rotational quantum number and b is the rotational constant. So here this is the rotational energy in terms of the centimeter inverse. So here let us consider the vibration energy in terms of the centimeter inverse. It is equal to V plus 1 half bracket complete omega bar. So here again V is the vibrational quantum number and omega bar is the fundamental vibrational frequency in terms of a centimeter inverse. So here epsilon Vj in centimeter inverse can be written as, so by adding these two, that is the rotational energy as well as the vibration energy in terms of the centimeter inverse, we get the equation number 1. So here epsilon Vj is equal to V plus 1 half bracket complete omega bar plus B j plus 1 bracket complete centimeter inverse. This is the equation number 1 where V is the vibrational quantum number, its value is 0, 1, 2, 3, and here the j is the rotational quantum number, again its values are 0, 1, 2, 3 and so on. So here this is the equation number 1. So friends, on inserting the appropriate value of the V and J, that is a value of the vibrational quantum number as well as the rotational quantum number in the equation 1. The values of allowed vibrational rotational energies can be obtained just by substituting the value of the V and J here in this equation number 1. Here we can find out the allowed vibrational rotational energy. So, let us consider the simultaneous change in the vibrational and rotational energy. So, here let a transition takes place from the lower rotational level. So, lower rotational level, it is denoted by symbol J double dash. In the lower vibrational level, that is a V double dash, to the higher rotational level J dash, in the higher vibrational level V dash. So, for this transition, the absorbed energy, that is a delta epsilon Vj in centimeter inverse, is given by considering the equation number 1. So, here this is the equation 1. So, here in this equation we have to substitute the value of the V and J. So, here delta epsilon, that is the energy absorbed during the transition, delta epsilon Vj. So, here in bracket V dash plus 1 half bracket complete omega bar. This is the V dash is the upper vibrational energy. So, symbol V dash is used for the upper vibrational energy level, that is the V dash, plus B into J dash plus 1. Again J dash, that is the higher rotational level, that is the J dash, minus, that is the V double dash plus 1 half omega bar. V double dash, it is the lower vibrational energy level, plus B into J double dash. So, here actually it is here J double dash plus 1. This is the equation number 2. So, again J double dash, it is the lower rotational energy level. So, here V dash minus V double dash. So, this is the V dash minus V double dash. So, here 1 half plus 1 half and here the minus 1 half, these two will be cancelled. So, here the V dash minus V double dash bracket complete into omega bar plus B, here J dash in bracket J dash plus 1, here there is a minus sign. So, minus J double dash, here J double dash, here plus 1. So, here the plus 1, this is the equation number 3. So, here energy absorbed, it is given by the equation 3 during the transition. So, here now in the fundamental vibrational transition, the selection rule for the vibration spectra, that is a delta V is equal to plus minus 1. So, here that is V double dash is equal to 0 to V dash is equal to 1. So, here the transition V dash minus V double dash is equal to 1, then the equation 3 can be written as, or equation 3 can be written as, here V dash minus V double dash is equal to 1. So, here in the equation 3, this is the V dash minus V double dash and its value is equal to 1. So, here equation 3 can be written as delta epsilon Vj is equal to omega bar plus B J dash in bracket J dash plus 1 minus J double dash. So, here J double dash plus 1 bracket complete. So, here the omega bar plus B, here J dash into J dash, that is a J dash square, plus J dash into 1, that is a J dash, minus J double dash into J double dash square minus J double dash. So, here rearrangement, that is a delta epsilon Vj is equal to omega bar plus B. So, here this J dash square minus J double dash square, this can be rearranged in this way, that is in first bracket J dash plus J double dash bracket complete, in the second bracket J dash minus J double dash bracket complete, plus that is a J dash minus J double dash. So, here J dash minus J double dash, then here is equal to omega bar plus B. So, here the J dash minus J double dash, it is taken as the common. So, here this equation can be written as J dash minus J double dash in the bracket, it is taken as the common. So, here in the second bracket J dash plus J double dash plus 1, this is the equation number 4. So, here the energy absorbed during the vibration rotation transition, delta epsilon Vj is equal to omega bar plus B in bracket J dash minus J double dash, in the second bracket J dash plus J double dash plus 1. So, here equation 4. Now, for the rotational transition, the selection rule is delta J is equal to plus minus 1. Again, similarly, as the vibration spectra, for the rotation spectra, all of you know that the selection rule is delta J is equal to plus minus 1. So, here there are two cases, delta J is equal to plus 1 as well as the delta J is equal to minus 1. So, let us consider one by one. So, the case first, delta J is equal to plus 1, that is J dash minus J double dash is equal to plus 1, or this can be written as J, from this equation we can write J dash is equal to J double dash plus 1. So, here the first selection rule, that is a delta J is equal to plus 1. So, here when the delta J is equal to plus 1, that is when the molecule is promoted to its higher rotational energy level by 1 unit due to the absorption of energy, equation 4 can be written as, that is a delta epsilon Vj is equal to omega bar plus B. So, here equation 4 can be written as, that is equation 4, here J dash minus J double dash. So, here the J dash minus J double dash it is equal to 1. So, here the value of this bracket it is equal to 1. Then here this can be written as J dash is equal to J double dash plus 1. So, here this is the J double dash plus 1, its value is J dash. So, here equation 4 can be written as B into 1 into J dash plus J dash. So, here is equal to omega bar plus twice B J dash. So, here again the value of the J dash, here it is a J double dash plus 1. So, this value can be substituted here, and here the final equation delta epsilon Vj is equal to omega bar plus twice B J double dash plus 1, where the value of the J double dash is equal to 0, 1, 2, 3, 4 and so on. This is the equation number 5. So, here when we consider the selection rule, delta J is equal to plus 1. So, here equation 5 describes the spectral line position in the vibration rotation spectrum, and it reveals that the corresponding lines are observable at higher side of the fundamental vibrational frequency omega bar for the different values of the J double dash. So, here the J double dash has the value 0, 1, 2, 3, 4 and so on. This shown in the diagram. So, here this group of the line is called as the R branch, and it is a label as the R0, R1, R2, R3, R4. So, here when the first transition takes place from 0 to 1, so the first line is obtained, that is R0. When the second transition takes place from 1 to 2, then the second R line is obtained, it is denoted by symbol R1. Then here the third transition 2 to 3, so here the line is in the spectrum, the line is denoted by the R2, similar way R3, R4 etc. So, here when we consider the selection rule for the rotational energy level, that is the delta J is equal to plus 1, we get the R line and they are denoted by the symbol R0, R1, R2, R3, R4 etc. in the rotation vibration spectra. So, this is the case number 1. So, let us consider the case number 2, that is the delta J is equal to minus 1. That is a J dash minus J double dash is equal to minus 1, or this can be written as J double dash is equal to J dash plus 1. So, here hence for delta J is equal to minus 1, that is when the molecule is lower down to its lower rotational energy level by 1 unit due to the net absorption energy. Again the equation 4 can be written as delta epsilon Vj is equal to omega bar plus B into minus 1. So, here J dash minus J double dash, its value is minus 1. So, here it can be written as a minus 1 multiply by in bracket J double dash plus J double dash. So, this can be written as is equal to omega bar. So, here J double dash plus J double dash, that is a twice J double dash. So, here minus twice B J double dash, and here the value of the J double dash, here it is a J dash plus 1. So, this value is substituted here, and the final equation is equal to omega bar minus twice B in bracket J dash plus 1 bracket complete, where the value of the J dash is equal to 0, 1, 2, 3, 4, and this is the equation number 6. So, here friends, when we consider the second selection rule, that is the delta J is equal to minus 1, at that time the energy absorbed, that is the delta epsilon Vj, it is equal to omega bar minus twice B in bracket J dash plus 1. So, here this is the equation number 6, and equation 6 describe the line position in the vibration rotation spectrum, and it reveals that the corresponding lines are observable at lower side of the fundamental vibrational frequency omega bar for a different value of the J dash. This is shown in the diagram. So, here this group of the lines called as P branch, and they are labeled as the P1, P2, P3, P4. So, here when we consider the first transition from 1 to 0, then here the line obtained in the spectrum, it is denoted by the symbol P1. The second transition, that is from 2 to 1. So, second line is obtained, that is the P2. Third transition from 3 to 2, so P3, and similar way P4, P5, P6 and so on. So, here friends, when we consider the second selection rule for the rotational energy level, that is the delta J is equal to -1 in the rotation vibration spectrum, we get the P types of the line, and they are denoted by symbol the P1, P2, P3, P4 and so on. So, let us consider the vibration rotation transition. So, here these are the lower rotational energy level. In the lower vibrational energy level, that is the V double dash, this is the V double dash, these are the lower rotational energy level, and they are denoted by symbol J double dash. So, 0, 1, 2, 3, 4, 5. So, here this is the vibration, higher vibration energy level, that is a V dash, and here these are the higher rotational energy level, they are denoted by symbol J dash. So, 0, 1, 2, 3, 4, 5. So, here there are two selection rule. So, here when we consider the R branch, the selection rule for the rotational energy level, that is the delta J is equal to +1, and when we consider the P branch, that is the selection rule, delta J is equal to -1. So, let us consider once again one by one. Delta J is equal to +1. So, this is the first transition from 0 to 1, because here selection rule is delta J is equal to +1. So, from 0 to 1 we get the first line, that is R0. So, here the transition is start from the 0 to 1, it start from the 0. So, the line R line, it is denoted by symbol R0. So, let us consider the second transition from 1 to 2. So, here the second line is obtained, second R line is obtained, and it is denoted by symbol R1. Then here 2 to 3, that is R2, 3 to 4, that is R3, that is 4 to 5, that is R4. So, here R branch delta J is equal to +1. So, here this is a R0, R1, R2, R3, R4 and so on. The second selection rule, that is for the P branch, delta J is equal to -1. So, here it start from the 1 to 0. So, here 1 to 0, then here 2 to 1, then here 3 to 2, then here 4 to 3 and here 5 to 4. So, here this line, it start from the 1. So, this P line, it is denoted as symbol P1. So, this is the P1, here this is the P2, here this is the P3, here this is the P4 and here this is the P5. So, here these are the transition, and here this is the vibration rotation spectrum. So, here the first line, when we consider the vibration rotation spectra, first line, that is the R1, it is obtained at the twice B centimeter. Here R2, it is this is R0, then R1, it is obtained at the 4B centimeter inverse, then 6B centimeter inverse, 8B centimeter inverse, 10B centimeter inverse. So, here the P line, that is the P1, again it is obtained at the twice B centimeter inverse. So, P2, it is obtained at the 4B centimeter inverse, then 6B centimeter inverse, 8B centimeter inverse, 10B centimeter inverse and the so on. So, here this is the band center, that is the omega bar, and here there is a gap at the band center, because here the 0 to 0 transition is not possible. In case of the rotation spectra, 0 to 0 transition is not possible, that is why there is a gap at the band center, and this distance is 4B centimeter inverse. While the distance between these two lines, it is a twice B centimeter inverse. Here also the distance between the two line, 2P line, it is a twice B centimeter inverse, but here distance between this P1 and this is a P1 and R0 line, that is a 4B centimeter. So, here there is a gap at the band center when we consider the rotation or vibration rotation spectra. So, here these are the various lines, that is R0, R1, R2, R3, R4, R5. So, here P1, P2, P3, P4, P5. So, here in this way the vibration rotation spectra is obtained. So, here it is clear that the spacing of the line is a twice B centimeter inverse, which allows us to calculate the moment of inertia and the equilibrium bond length. So, friends, here all of you know that when we know the spacing between the two rotational line in the spectrum, so here from that we can find out the B, and if we know the B, So, here B is equal to h upon 8 pi square IC. So, from this here we can find out the moment of inertia, and once when we know the moment of inertia, from the moment of inertia we can find out the bond length, because here I is equal to mu into r square. I is the moment of inertia, mu is the reduced mass for the diatomic molecule, and here we can find out the bond length. So, here the band origin will be at omega bar. So, here this is the band origin. So, here this is the band origin, it is at the omega bar. So, here from the band origin, so here we can calculate or we can find out the force constant, that is the K, because K is equal to 4 pi square omega square into mu. So, here all of you know that omega is equal to C into omega bar. If we know the omega bar, here we can omega bar is equal to omega upon C. So, we can find out the omega, just substituting the value of the omega here and the reduced mass, here we can find out the force constant for the diatomic molecule. So, here the IR study gives us information regarding the structure as well as the rigidity of the diatomic molecule in the gas phase. So, IR spectrum is generally used in the identification of the functional group in organic compound. This identification is useful in the structural determination of the steroids, hormones, pharmaceutical chemicals, liquids, carbohydrates, amino acids, proteins, nucleic acid, enzyme, etc. So, these are the important application of the or important uses of the IR spectrum. And lastly, let us discuss the vibration rotation spectra of the carbon dioxide molecule. So, friends, all of you know that carbon dioxide molecule is the non-polar molecule. So, here when we consider the non-polar molecule, they does not give the microwave spectra or they does not give the rotation spectra. Just to obtain the rotation spectra or the microwave spectra, the molecule must possess the permanent dipole moment. So, here the carbon dioxide molecule, it does not give the rotation spectra, but it gives the vibration rotation spectra. So, here the condition for the observing microwave or rotation spectrum is that molecule must possess a permanent dipole moment. And here when such a molecule or when the molecule electrical moment rotate, it generate an electric field which can interact with electric component of the microwave radiation, and during interaction energy can absorb or emitted, and thus rotation of molecule gives rise to a spectrum. So, if molecules are not having the dipole moment, interaction is not possible and these molecules are said to be microwave inactive. So, here the carbon dioxide molecule does not possess permanent dipole moment. So, carbon dioxide does not show the rotation spectra. So, here vibration spectra are exhibited by the diatomic molecule with or without a dipole moment. So, here the exciting IR radiation can induce an oscillating dipole moment in their own, and hence this can undergo the vibration rotation transition. So, friends, here once again to obtain the vibration spectra, generally the molecule must have the permanent dipole moment. So, here carbon dioxide molecule, it is a non-polar molecule, it does not have the dipole moment, but what is important? So, here when the carbon dioxide molecule, when it interact with the IR radiation, so exciting IR radiation can induce an oscillating dipole moment in the carbon dioxide molecule. So, here hence this can undergo the vibration rotation transition. So, the oscillating dipole moment in these molecules or in the carbon dioxide molecule are induced during their stretching and bending vibration modes. Therefore, the carbon dioxide show the vibration rotation spectrum. So, friends, here carbon dioxide molecule, it does not give the rotation spectra, but even though it is a non-polar molecule, it gives or it shows the vibration rotation spectra because of the induced oscillating dipole moment during the interaction with the IR radiation. So, here friends, in today's lecture we have discussed the vibration rotation spectra as well as the vibration rotation spectra of the carbon dioxide molecule. Thank you.